So next week is the final exam, starting Monday. And you should have read the information from Dr. Naj. You can use 3 single-sided help sheets, one from exam 1, that was weeks 1, 2, 3, 4, 1 page from exam 2, weeks 5, 6, and 7, and then you'll also need a 3rd help sheet for the last 3 weeks, weeks 8, 9, 10. This is week 10 today. A good place to look up the equations to put on the help sheets is in the exam study guide, which you find at the end of each chapter. So look through the exam study guide and make sure you understand the equations there and write them onto your help sheet for each of the chapters. Now, I'm also going to hold another Zoom meeting this week. It'll be Friday at 4 p.m. Friday, unlucky 13 at 4 p.m., the usual meeting ID. And I'll go over some of the practice exam questions. So you will have a practice exam. You can practice doing the kind of questions that'll be on the final exam. And I'll go over some of those questions. Maybe I won't solve them completely, but I'll show how they would make use of the basic equations. The main thing for tonight is to take a look at some of the problems that are due Thursday, on special relativity. So this is chapter 35. Let me start by just writing the fundamental equations. These are the kind of equations you might have on the help sheet. First of all, the Lorentz transformation relates coordinates of space and time for different frames of reference, different inertial frames. So suppose we have an inertial frame F with coordinates x and t, and then moving with respect to F, we have another frame F prime with coordinates x prime and t prime. So here's the x, y coordinates, and then there's a z coordinate perpendicular to that for the frame F. Here are the coordinates x prime and y prime for the frame F prime. I could think of the frame F as being the Earth frame of reference, and the frame F prime being a moving frame, moving meaning moving relative to the Earth. Let's say the relative velocity is v in the x direction. And then there are transformation equations that relate the different coordinates. So for example, x, in going from F to F prime, x is transformed from x to x prime, which is gamma x minus vt, where gamma is 1 over the square root of 1 minus v squared over c squared. The coordinates perpendicular to v do not change. So y prime is the same as y. And z prime is the same as z. As far as the space coordinates are concerned, it's the coordinate parallel to the relative velocity which transforms in this way. Now the time also changes. So an observer traveling along in the frame F prime will be observing time intervals which are different than the time intervals observed by the observer at rest on the Earth. So that's one of the surprising features of special relativity. Time is not a universal parameter or coordinate. Time is different for different people, for different observers. And the transformation is, in going from frame F to frame F prime, T changes into T prime, which is given by gamma T minus Vx over C squared. All right, so that's the Lorentz transformation. And if you've read the book or if you've watched the screencasts on YouTube, you've seen how that transformation ensures that the speed of light is the same in all inertial frames. So an observer in the Earth frame of reference watching light travel will see it traveling at a speed c, and an observer measuring the speed of the same light wave will also see that light wave traveling at the speed c. Now, one equation you'll certainly be using is the addition of velocities. So here's the formula. If you have V1 is the motion of a frame of reference, let's say, and V2 is the velocity of an object in that frame of reference, then V, the velocity as it would be measured in the Earth frame, is V1 plus V2 over 1 plus V1 V2 over C squared. And this is an equation which you'll use in some of the Kappa problems, and probably also, or maybe also in one of the exam questions. The interesting feature of this combination of velocities is not really addition of velocities. It's not simply the addition. It's the combination of velocities. And one of the interesting features is that if V2 approaches C, then in the numerator you have V1 plus C. In the denominator you have 1 plus V1 divided by C. The numerator over the denominator, that's V, approaches C. So an object moving with velocity C in frame F prime also moves with velocity C in frame F. And of course, the only object that can move at the speed c is a pulse of light. So this is again an indication that light travels at the same speed in all inertial frames. But this is the equation for any objects where you have a relative velocity v1 and then a velocity of the object in that frame of reference of v2. This will be the velocity of that object in the other reference frame. And then the other part of chapter 35 has to do with momentum and energy. You know, these are properties of space and time. Well, the other part of the chapter is about momentum and energy, relativistic momentum and energy. The equations for momentum and energy are different in special relativity than they are in Newtonian mechanics. And in particular, for a particle with velocity u in some frame of reference, I better not call it v because I'm using v to stand for relative velocity of different frames of reference. So let me say u is the velocity of an object in some frame of reference. In that frame of reference, the equations for momentum and energy are P is equal to m times u over the square root of 1 minus u squared over c squared. You remember in physics 183, classical mechanics, momentum is just mass times velocity, m times u. But in reality, in special relativity, it's mu over the square root of 1 minus u squared over c squared. Of course, if the speed is small compared to the speed of light, then this quantity u squared over c squared is approximately 0. And so you're back to the classical formula, mass times velocity. And as for energy, well, energy in special relativity has two parts, mass energy and kinetic energy. And the total energy is mc squared over the square root of 1 minus u squared over c squared. If the particle is not moving, if u is 0, then E equals mc squared. So that's mass energy. But if the particle is moving, then the energy will be larger than mc squared. It has an additional energy, which you might think of as kinetic energy. These two formulas satisfy the condition E squared minus P squared C squared is m squared C to the fourth. All right, so those are the kind of equations that you'll find in the homework assignment this week. And so let's take a look at some of the problems. This problem says the mean lifetime of a muon in its rest frame is 2.2 times 10 to the minus 6 seconds. You have to understand a muon is an elementary particle, somewhat like an electron, but more massive than an electron, and unstable. A muon will decay into a neutrino, an electron, and an antineutrino. So a muon, if you have a muon, it doesn't last forever. In the frame of reference where it's at rest, it lasts for 2.2 microseconds. You can create muons in various ways, but in particular, they're created by collisions between cosmic rays and atmospheric molecules. But they don't last forever. They only last 2 microseconds. 2 microseconds in their rest frame. But if a muon is created by a collision of a cosmic ray with an atmospheric molecule, it will be moving very fast. So the first question is, what's the lifetime in a frame of reference in which the velocity of the muon is 99% of the speed of light? C is the speed of light. So, for example, in the frame of reference of the Earth, where the muon has been created by a cosmic ray collision in the upper atmosphere and is moving very, very fast, approaching the speed of light. So that's part A. And that's an example of time dilation. So the question is, what is delta t, the time interval from the creation of the muon until it decays in the frame F? I call it here the lab frame, but I could think of it as the Earth frame of reference. So you'll need to know the equation for time dilation. And that's one of the equations you'll have on your help sheet for the exam. Time interval in a frame F compared to the time interval in a frame F prime, which is moving with velocity v, delta t is gamma delta t prime, where gamma is that quantity 1 over the square root of 1 minus v squared over c squared. So gamma is 1 over, this is something you'll have to remember, the 1 over the square root 1 minus v squared over c squared. So that's a number greater than 1. It's approximately equal to 1 if v is small, but if v is getting to be a significant fraction of the speed of light, then gamma will be large, and so the time in the Earth frame of reference will be much longer than the time in the rest frame of the muon. Now, you know this equation from the book, so you don't have to prove it, but you don't have to derive it on the exam. But just to prove this, it comes from the Lorentz transformations. You know, this is the transformation of time. This is the transformation of position. Now, the primed frame is where the muon is at rest. So delta x prime will be 0. X prime doesn't change. The muon is not moving in the x coordinate, x prime coordinate. So if x prime is equal to 0, that means x is vt, or this is a misprint, delta x is v delta t. Well, that just says that the particle is moving with velocity v. But the question is, what's the time? So now let's calculate delta t prime. Well, it'll be gamma times delta t minus v over c squared delta x. Delta t minus v over c squared delta x. And delta x is v delta t. So I have another factor of v and change delta x to delta t. Delta t prime is given by this expression. Now I can factor out delta t. So here's delta t. I have gamma, which is 1 over the square root, 1 minus v squared over c squared. And then I'll have this factor, 1 minus v squared over c squared. So I have that 1 minus v squared over c squared divided by the square root of 1 minus v squared over c squared. So that will be the square root of 1 minus v squared over c squared times delta t. Or now writing it as delta t, this is 1 over gamma. So if I multiply both sides of the equation by gamma, delta t is gamma delta t prime. That's where this time dilation equation comes from. It's just a property of the transformation between coordinates. Now, you know, on the exam, you can just have this on your help sheet and immediately apply it, or on this problem for that matter. So delta t would be delta t prime divided by the square root of 1 minus v squared of c squared. So it'll be 2.2 microseconds. That's delta t prime over the square root of 1 minus 0.99 squared. That's about 14 microseconds. So the lifetime in the Earth's frame of reference is much larger than the 2.2 microseconds. Well, it's 7 times larger, roughly. Now, part B proposes that it's moving even faster. And then the question is, how far does it move? So part B of the homework problem is, so in part B, what will the co-moving observers measure as the length of the meter stick? Well, a meter stick is 1 meter long in the frame in which it's at rest. So the answer to part B is very simple. Co-moving with the meter stick, they'll measure the length of the meter stick as being 1 meter. But the observers observing the meter stick moving will see it as less long, less than 1 meter. Not by this equation, because that's only for the x coordinate. But the x length will be contracted. That's the length contraction. The y length will not be contracted. So there'll be a shorter x length, an equal y length. And so the overall, by the Pythagorean theorem, the overall length will be less. This equation is only for a length which is, for motion which is along the length. In other words, where the velocity is parallel to the moving object. Parallel to the length of the object. So, you know, you'll have this equation on your equation sheet, but you have to understand what it means, because in this problem, there's contraction in one direction, but not in the other direction. So you have to think a little bit. This equation applies to the x coordinates only, but not to the y coordinates. Right, so we've seen time dilation, we've seen length contraction. Here's an example with addition of velocities or combination of velocities. It's kind of a science fiction example. It's not something realistic. A rocket ship approaches a planet at a speed alpha times the speed of light. That's the speed relative to the planet. So here's the rocket moving towards the planet. Here's the planet with a speed v. Let's call that v1, which is alpha c. That's the speed relative to the frame of reference of the planet. It fires a missile toward the planet with a speed beta c relative to the rocket ship. So here's the missile, which is fired towards the planet with a speed v2 equal beta c, but that's the speed relative to the rocket, not the speed relative to the planet. Now the question is, what's the speed of the missile relative to the planet? In other words, for an observer on the surface of the planet who is at rest with respect to the planet and observing the distances and times of this missile, what will that observer measure as the velocity of the missile? Now, in classical physics, you would just say, well, it'd be v1 plus v2. So sometimes this is called addition of velocities. But that's for classical physics. For the relativistic addition of velocities, it's not simple addition. It's really a combination of two velocities given the Lorentz transformations of the space and time coordinates. So that's where we had earlier in the screencast the formula for addition of velocities. It's usually called addition of velocities, which is a little bit of a misnomer because it's not just addition. It really should be called combination of velocities. The frame of reference of the rocket is moving with velocity v1. The frame of reference of the missile relative to the rocket is v2. So the frame of the reference of the missile relative to the planet is v1 plus v2 over 1 plus v1 v2 over c squared. So we've had time dilation, length contraction, combination of velocities. Here's another problem involving momentum and energy. What's the speed of a particle whose momentum is mass times the speed of light? You know, in Newtonian mechanics, momentum is mass times velocity. But in relativity, momentum is not mass times velocity. The velocity of a particle can never be c. A massive particle can never travel as fast as light. So we're not saying that the speed is c. We're saying that the momentum is m times c. Then what is the speed for the momentum m times c? And for this, you need to know momentum is mass times velocity over the square root of 1 minus u squared over c squared, where u is the velocity of this particle. That's what you're trying to calculate. All right, so you have this equation. The m's cancel, so it doesn't matter what the mass is. Now we're going to solve for u. Well, okay, this is just a bit of algebra. We solve that equation for u. And it'll be given as some fraction of c. So that's the first part of the homework problem. The second part of the homework problem is unrelated, completely different question. How much work is required to accelerate a proton from rest to a speed kappa times c. Now you have to know what kappa is. So kappa would be given in the problem. So kappa is some given amount. It has to be a number less than 1. So that would be given in the problem. Now, remember the relation between work and energy. Work is a transfer of energy. And the change in energy is equal to the amount of work that's done. I'm not saying how this work is done, but maybe there's a rocket or something which is accelerating this proton. So I'm not saying how the work is done, but I'm saying how much work is done. Enough work to accelerate the proton from rest to a speed kappa times c. Okay, so we're going to say, well, the amount of work is the change in energy. The initial energy is mc squared, where m is the mass of the proton. The final energy is mc squared over the square root of 1 minus u squared over c squared. Now u is kappa c. So I guess u squared is kappa squared, c squared. So there's a bit of a misprint here. The denominator we have to have mc squared over the square root of 1 minus kappa squared. Speed is kappa c. So v squared over c squared would be kappa squared. Now the question is how much work is done? Well, that's given by the change in energy. The final energy minus the initial energy. The initial energy is mpc squared. This is something bigger. There's a larger number. And so E final minus the initial is some positive amount of work had to be done to create that much kinetic energy. All right, now kappa will be given in the problem. You also need to know the mass of the proton. And there's an easy way to do this, and there's a hard way. The easy way is to write down the mass of the proton in electron volts divided by c squared. The hard way to do it is to write down the mass of the proton in kilograms. It doesn't really make sense to use kilograms to describe the mass of something as tiny as a proton. You could do it that way, but that's the hard way to do it. So let me just explain how you would look up the mass of the proton in electron volts. It's a problem taken from the textbook. It's exercise 87 in chapter 35. It's a little more difficult than the other problems. Suppose a particle, let's just say it has mass m, has a constant acceleration. That's the acceleration as experienced by the particle. So in other words, in a time interval delta tau, or d tau, an infinitesimal time interval d tau, where that's the time as observed by the particle, as observed in the particle's frame of reference, if the change in velocity is a constant g times d tau, then we say the particle has constant acceleration g. It's the acceleration in a frame of reference of the particle. So this d tau is called the proper time interval. It's the time interval in the frame of reference which is at rest with respect to the particle. Now the particle's velocity is increasing. So that frame of reference is changing in time. So this is a particular frame of reference where instantaneously the velocity is v and the velocity change is dv. So I call it dvi. It's the instantaneous change in velocity as measured in the instantaneous rest frame. So we're saying there's a constant acceleration. We'll call it g, but I don't mean to suggest that it's the acceleration due to gravity on Earth. That's just the letter that I'm going to use for the constant acceleration. dvi will be the velocity increment as measured in the instantaneous rest frame. So that's why I call it dv sub I. It's in that frame of reference where instantaneously the particle is moving with velocity v. And then d tau is the square root of dt squared minus dx over c squared. That's the proper time. Again, well, we're going to see in a minute that's related to time dilation. This is the equation which this is really a different form of the time dilation equation. So t and x are time and space coordinates in the Earth's frame of reference. But the particle is moving with respect to the Earth with a velocity v, which is changing in time. And the first part of the problem is to derive a differential equation for v, the velocity of the particle, as a function of time t. Meaning the velocity in the ground frame, the inertial frame of which the initial velocity is 0. So let's see if we have a picture here. Yeah, here's a picture. Again, there are two frames of reference at any time t, but in fact, there are an infinite number of frames of reference as the particle accelerates down the x-axis. Here is the Earth frame of reference, or the ground frame of reference is what Bauer and Westphal call it. There's a coordinate x in the direction of the motion, and there's a perpendicular coordinate y. There's also a perpendicular coordinate z, but I can't draw the third direction. Now, these red coordinates, x prime and y prime, are the coordinates in the frame of reference where the mass is instantaneously at rest. In other words, this coordinate system, the primed coordinate system, is moving with a velocity equal to the velocity of m at the time t that I'm interested in. All right, now I want to consider a later time, t plus delta t. So what will be the velocity of m at a later time, t plus delta t? Well, that's an example of addition of velocities. This mass is moving with velocity v at time t. It's given an additional velocity dvi relative to this frame of reference. So the formula for addition of velocities, or more properly, combination of velocities, is v of t plus dvi. That would be the classical result. But you have to divide by 1 plus v times dvi over c squared to get the true result for physics. And again, dvi is g d tau. And d tau is the proper time. So d tau is the square root of dt squared minus dx over c squared. I can factor out dt from the square root. So I have dt times the square root of 1 minus dx over dt squared divided by c squared. And dx over dt is v. That's just velocity. So v squared over c squared. So d tau is dt squared root of 1 minus v squared over c squared. That is time dilation. You see, dt is d tau over the square root of 1 minus v squared over c squared. So the time interval in the Earth frame of reference is longer than in the particle's frame of reference. But the particle's frame of reference is constantly changing as it accelerates. So this is just the formula for d tau at this instant when the velocity relative to the Earth is v. So this is nothing but the time dilation equation. So this is the addition of velocities equation. This is the time dilation equation. All right, so that's not quite finished part A. Now we want to derive an equation for a differential equation for V. Well, we can use this to calculate dv dt. So dv is v of t plus tau, t plus dt, minus v of t, that's change of velocity. The velocity after the time d tau minus the velocity before the time d tau. And by this equation, that is dvi. If it weren't for this denominator, it'd be very simple. V at t plus dt minus v at t would just be dvi, just be dvi times 1. But we have this extra factor. I really have to multiply both sides of the equation here by the denominator. So when I subtract v of t, I subtract, I'm left with dvi, but I also have a change over here where I have v times dvi over c squared. So that'll be dvi times v squared over c squared. So there's a bit of tricky algebra here. If you multiply this by this side of the equation and then combine v t plus dt times v of t, just call that v squared. I'll have here 1 plus v squared over c squared times dvi. Move that back to the other side of the equation. That'll become dvi times minus v squared over c squared. Now dt is d tau, 1 minus v squared over c squared to the minus 1/2. That's the time dilation equation. That's this equation. dt is d tau divided by, or times 1 minus v squared over c squared to the minus 1/2. Now I take the ratio dv divided by dt. So it's this quantity. It's dvi, that's g d tau. And now I divide by this quantity. No, I have dvi times 1 minus v squared over c squared. dvi is g d tau. So I have g d tau times 1 minus v squared over c squared, d tau over dt. But d tau over dt is 1 minus v squared over c squared. To the minus 1/2 dv divided by d tau. No, dv divided by dt. Let's see if I got a mistake here. I have one factor of 1 minus v squared over c squared. Oh yeah, when I divide by this, I get another factor of 1 minus v squared over c squared to the 1/2. So those combined do 1 minus v squared over c squared to the 3/2. If I can blow this up a little bit. So the equation, the differential equation that it's referring to in part A is this equation. dv dt is g 1 minus v squared over c squared to the 3/2 power. Now you can solve that differential equation by separation of variables. You solved differential equations back in physics 183. So you know how to solve this equation. You divide this side of the equation by the v-dependent factor. You multiply this side of the equation by the t-dependent factor. And then you integrate both sides. So on one side, you'll have g times t. On the other hand, on the other side, you'll have the integral dv over 1 minus v squared over c squared to the 3/2 in the denominator. Well, we better not call that v because v is the endpoint of the integral. Let's call it v prime. So I'll have the integral dv prime over 1 minus v prime squared over c squared to the 3/2 power. Well, that's an elementary integral. That's v over the square root of 1 minus v squared over c squared to the 1/2 power. And that's equal to g times t. So that pretty much solves part B of the problem. Find v as a function of t. So that's the velocity and the time in the Earth frame of reference. Well, what I have is the time as a function of velocity. I want the velocity as a function of the time. So I have to do a bit of algebra here to solve for v. V of t is gt over the square root of 1 plus gt over c squared. So that answers part B of the question. Solve for v of t. There's an interesting feature here. In the limit t goes to infinity, in the denominator I could neglect the 1 because gt over c is becoming infinite. So gt over c is becoming very large. 1 is negligible. Then I just have gt divided by gt over c. So v approaches c. So if a particle has constant acceleration, its velocity will increase but never reach the value of c, the speed of light. It would take an infinite time to reach the speed of light. So there's another example why it's not possible for a massive particle to travel at the speed of light. The time it would take to accelerate it to the speed of light is an infinite amount of time. All right, well, that's parts A and B. Now, once you've got part B, you should be able to do the rest of the problem. I guess it should be C, D, and E, but it's written here as D, E, and F. But anyway, the 3 more parts of the problem. For this part, you have to calculate x as a function of time. Well, x is just the integral of v. You have the equation for v, so you should be able to do the integral. And then, well, just for the sake of curiosity, let's suppose g is 9.81 meters per second squared. How long would it take to accelerate to a speed v final? And I guess the value of v final must be given in the problem. And similarly, how far would it have to travel in order to reach the speed, some final speed? Maybe the final speed is, I don't know, 90% the speed of light. How long would it take to accelerate up to 90% of the speed of light? How far would it have to travel to accelerate up to 90% of the speed of light? So that's the problem from the textbook. It's the final problem on the long Kappa assignment. A particle moving with a constant acceleration. The problem in the book is not exactly the same as this, but it's really the same problem. It's just that it's written in a slightly different way. But you can get some hints about the problem by reading this exercise 87, where the authors give some information about, well, some of the information which I've already gone over here. All right, so that's everything that I had prepared for the homework assignment that's due, I guess, Thursday. And Friday the 13th, I'll have another Zoom meeting with some, discussing some of the problems on the practice exam. You should definitely do the practice exam to prepare for the final exam. Make sure you can do those practice exam problems, because the problems on the final exam won't be exactly the same problems, but they'll be similar. And so that'll help you get those problems in your mind. But don't forget, the final exam will include also the earlier part of the semester. So I would say your biggest challenge for the final exam, since it's coming due on Monday, well, you have to, you can start doing it on Monday, is to get that set of 3 help sheets I mentioned at the very beginning. Prepare those 3 help sheets. It's almost 8 o'clock. Any questions?
Oh, I got a quick question real quick for
Okay.
the muon decay problem.
The muon decay problem, yeah.
So for part B, when it was calculating the distance it travels, you would do the velocity, which is just 0.99 times the speed of light times dt. And is that just the 2.2 times 10 to the negative 6?
No,
Or that,
that's this DT.
oh, is that the dt we found in part A then?
Yep, that's this is the velocity in the Earth frame of reference. This is the time in the Earth frame of reference. This then will be the distance in the Earth frame of reference.
All right, thank you.
So you have to use the same coordinates for one frame of reference. You have to say, am I talking about the distance relative to the Earth? Yes, what's the mean distance that a muon will travel? That means relative to the Earth.
All right, thank you.
Okay, so I will now end the meeting.